Hello, and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you and have you step into my virtual classroom as I teach you something about math today. This is day 2 within the sequence bit. This is going to be on constructing arithmetic sequences. So we've been doing, we took equations of sequences and we made sequences out of them. We made the list of numbers. Now you're going to take a sequence and make its equation. They will be the arithmetic sequences that we determine, and we'll be using explicit form and recursive form. I have 21 practice problems for you today, and a lot of them get a little bit redundant, which is, kind of good and bad. Not much variety, but good reteachings, and it probably means I can get it done a little bit faster. I do have 21 practice problems to go through with you guys, and alongside that, I'm being time conscious because I got some Sunday football behind me right here playing the Red Zone channel. Thank goodness the NFL probably doesn't peruse my math channel, otherwise they'd give me quite a few copyright strikes, I'm sure. But it is blurry. I tend to be small in the background anyway, so I sure hope that there's nothing on that. And just don't report me, please. So I'll go ahead and get started here with number 1. Here we go. Farah pays a $25 sign-up fee to join a car sharing service and a $7 monthly charge. The total cost of using the car sharing service for N months can be found using this model here. This is an equation and it is a function. The table shows the cost of the service for 1, 2, 3, and 4 months. Complete the table for this and what are domain and range of the sequence. We use the word here. What is the common difference? Okay, so just to make sense of the equation to start, $25 sign-up fee is existing right here. She only has to use it once. That's why 25 just shows once right there, not by a variable. $7 per month thereafter depends on the number of months. If she pays for 10 months, it's going to be 7 times 10, things like that. So the cost is a function of the number of months that she chooses to use, and she pays them just at the end of a month, just 1 month, 2 month, 3 month. That's kind of what makes this a sequence. In other words, halfway through the month, she's not like, well, I'm going to pay $350. She does 7 at the end or at the start of a month, whatever it is. Cost service for 1, 2, 3, and 4 months. Complete the table. Okay, so in order to find out when n is 1, this is for part A, when n is 1, we're going to go C of 1 equals 25 plus 7 times n, which is 1, 25 plus 7, which is 32. So this is kind of more in the explicit form right here. For 1 month, she'll be paying $32. And then C of 2 is going to be 25 times 7, plus 7 times 2. Let me do that again. And the benefit of using something with explicit right here is that you get to see exactly what goes in and what comes out in the sense. When 2 goes in, this number comes out. That's how explicit works. The downside is, unless you know completely how they work on a recursive sense, you got to compute this thing over and over. It's likely that you see what's going on, though, as I'm computing these. It looks like that $7 is going to be added every month. I mean, that's what they say right here. But when it comes to this, if I'm showing these computations for an explicit sequence, it's plainly seeing how explicit functions are generally used. But again, if you know what's going on from one value to the other, you could also construct this and say, hey, it appears that I'm adding $7 each month. Therefore, 7 is kind of representing what's called my common difference. Now, the reason why I'm mentioning this right now is because this section is going to be all about constructing arithmetic sequences. This one is kind of a the backwards approach. This one we're writing out the list based on the equation, but today we're going to be writing equations based off lists, except for this one. But this goes to show, if I have a common difference right here, I could ipso facto help create my equation and figure out, oh, 7 gets multiplied by my position value. Okay, what are the domain and range of this sequence right here? Domain is the inputs. Those are the n values. So the domain of the sequence is 1, 2, 3, and 4. It says she uses it for 1, 2, 3, and 4 months. Or it says that the table shows that. Let's see. Total cost. I'm going to put a ... in case to show that she could do more months thereafter. 1, 2, 3, and 4 would probably be fine for Farah. And then range, this is how much she spends for those 1, 2, 3, and 4 months, and probably so on and so forth. This pattern, this is an arithmetic sequence because it's a common difference. This continues with a linear path. So you'd keep adding 7 for each subsequent month there. What is the common difference, D? I just mentioned that a couple times there. That is 7. D equals 7. That's this value right here. It's the number that you keep adding from one value to the next as the position increases by 1. Okay, so that's number 1. Just going to go and move on to number 2. This is where we start to talk about what sequences are arithmetic, and when we find out which ones are, eventually we will be making equations out of them. All right, so tell whether each sequence is an arithmetic sequence. Basic nature is the the difference between terms needs to be common. Subsequent terms, that is. So 6 plus 1 is 7, 7 plus 1 is 8, 8 plus 1 is 9, 9 plus 1 is 10. Clearly it is an arithmetic sequence based on what I put right there. And I don't want you to just say yes if you were like my student, for example. I want you to give reason as to why. And this is reason enough for me. The common difference is 1. I say yes there. I'll go and write it down here. Yes, the reason, again, it has a common difference of 1. Part B, a little bit different what's happening here. Looks like I got plus 5, plus 10. From this point, I could actually stop and say this is not an arithmetic sequence. It does not have a common difference. Is there some sort of pattern here, though? Plus 15, plus 20. It looks like the difference is 5 more than it previously was, which is that's some sort of sequence of some sort of pattern description. In this case, not quite an arithmetic sequence, though. So no, there's no common difference we can tell. I'll put no CD. Okay. And that's essentially what's going to happen each time here. Here it looks like we're adding a -1, or I should say subtract 1. Then from -1 plus 2 is 1, minus 3, and plus 4. Interesting alternating sequence there. Not common. Not even, not arithmetic in that sense. It's not the same number over and over. And it does alternate. If it said plus 1, minus 1, plus 1, minus 1, that also wouldn't be arithmetic. That's not a common difference either. Part D. Let's see, use purple. Part D, I got plus 15, and clearly not plus 15 again. I could tell you what these numbers actually were, though, if I thought hard enough about it. If I did. I'm not sure. I know there's 1 squared, 4 squared, 9 squared. Oh, interesting. 25 squared. Something's kind of skipped here that I can't think about. But anyway, no common difference, clearly. 16 plus 65 is 81, and it kind of keeps going. So part D, clearly not an arithmetic sequence. Again, no common difference. And again, all it takes is 2 different ones, or 1 different one, to determine that it's not common. And finally, part E, looks like I'm subtracting 2, and just to confirm it's going to be that way the whole time. Yes, minus 2 each time. So yes, it's arithmetic because it has a common difference of -2. So that's good affirmation. Anytime it is arithmetic, you need the common difference anyway to do something else with it, like make the equation, come up with another position, something like that. Okay, number 3. A chemist heats up several unknown substances to determine their boiling point. Use the table to determine whether the sequence is arithmetic. If it is arithmetic, write an explicit rule and a recursive rule. Explicit and recursive for the sequence. If not, explain why it's not arithmetic. So same kind of thing as before. You can't write a rule for something that doesn't have a sequence tied to it. At least you can't write an arithmetic rule for an arithmetic sequence that's not tied to it. So let's see if it is arithmetic. I'm adding 35. If you don't know how to figure out what you're adding, I mean, clearly you can see this number here, but it is called a common difference. So for example, if I subtract one number from the one before it, you can tell it's 35. Let me show it that way here. If I do 149 minus 135, looks like I'm going to get 14. Which, as we're just going from one value to the next, doesn't appear to be a common difference here. So already I can explain why it's not arithmetic in that sense. Moving forward, we could keep subtracting, and it looks like, no, it doesn't look like we have a common difference here. So not arithmetic because from one term to the next, and there is an assumption we have to make, well, not an assumption, but from how I'm writing it, I'll explain it in a second. From one term to the next, there does not exist a common difference. Okay. Now, the thing that I wanted to mention was that the previous problem that I did, there does not exist the previous problem that I did with parts A through E, notice that the numbers were written as a list. Okay. The numbers before here were written as a list. So I have to play under the almighty assumption that, I mean, this one maybe not as much, but that this is probably the first term. But even if it wasn't the first term, I have to play under the almighty assumption that the terms that I'm looking at thereafter are absolutely the subsequent terms. What I mean by that is that this is the term that exists right after this one. So if this is the first term, this has to be the second term. Things like that. On this problem, I don't have to assume that this is the first term and second term and such, because now it's a table. What matters is what the n values are here now. And as long as these ones go in successive order like this, each value after is one more than the next, then I can go based on the conclusion that these are immediately one right after another. But if this didn't say a 2, say that this said a 12, suddenly this is going from 1 to 12, and you're going to have to play under a thing that, this is going to be harder to talk about, but from 1 to 12 plus 35 is a lot different from 12 to 13 being plus 14, and you have to play with that notion of what's the constant rate occurring in between. So make sure that if you're in a table, that the numbers are going one after the other to really, really make your claim. Okay, numbers 4 through, I don't know, maybe number 9 or so. The next few problems are kind of all the same thing. Write a recursive and explicit rule for the arithmetic sequence described by each table. I think we get to now happily play under the assumption that all of these will be arithmetic. So now that we're going to be doing arithmetic ones and writing the rules, let me, for this first problem on the side here, write out what kind of rules we're talking about here. A recursive rule relies on the value before it to get your next value. What I mean by that is, in order to get some f of n, to get some value here, I'm going to take the value before it. And that's what that means, f of n minus 1. If this is n, this is n minus 1. So if this is f of n, this is f of n minus 1. I'm going to take the value before it, and I'm going to apply my common difference. If it's arithmetic, I'm going to apply my common difference. It looks like that. So let's do the recursive form with this. Really what I really just need to find out what d is. Okay, so my common difference here looks like 3 is being subtracted each time. And I'm just going to use 2 to confirm it right now. They said it's arithmetic. Let's trust it. Minus 3. So my common difference here is negative 3. So I use that to make my recursive equation. I'll just call it r. For the recursive form, it's going to look like f of n equals f of n minus 1 minus 3. Couldn't be simpler than that, really. Plus d is plus negative 3 is minus 3. Couldn't be much simpler than that, really. But what I do need you to fully get as well, though, is that if I just told you to make me a list by subtracting 3 from one number to the next, you're like, got it, I know what to do. That's great. But where do you start subtracting 3 from? Right? We can't just assume it's 0. We don't just start negative 3, negative 6. I have to give you a place to start as well. So as much as the recursive form is that simple, I have to also alert what one of the values is. Specifically, the first term would be ideal. The first term is 35. So for recursive form, it says 2 bits. It says starting from 35, to find the next value, let's take the value before it and subtract 3. Okay. Now, I have a whole video before this one, I think, on doing these kinds of problems here. So they gave us the equation, and then I gave you the sequence. So if you want to see more on that being constructed, that's fine. Here, we're constructing the equation. So anyway, that's the recursive rule. The explicit rule, I think what I'll do is I'll copy and paste this little bit that I'm writing right here onto each slide. The explicit rule, I already said this before, it is based on your term's position. You determine what the value is based on the positional value, like based on n itself. N is literally used to compute it. And there's more than one way to write it. The one that I'm kind of going to be focusing on is this one. It does what I say tells the best story as far as what to do. This is the least memorizing-ish version if you know what this is saying right here. I'm going to write a dot to indicate multiplication so you don't think of it as a function. D is a common difference, n minus 1 is a quantity, and I'm multiplying here. So here's what this says. To find the value of some term, what I'm going to do is take the first term, and I'm going to add my common difference a certain number of times. N minus 1, I'll show you what that means here in a second. If I wanted to find out what the value of the fifth term was, as 23, I would start from this first term, and I would subtract 3 once, twice, 3 times, 4 times. I'd be subtracting 3 4 times to find the value of the fifth term. That seems to make sense. 5 is n, 4 is n minus 1. If I'm starting from the first term and I got to find the fifth term, it just takes 4 times because I'm starting from the first term. 2, 3, 4, 5. 2, 3, 4, 5. To get to the fifth term, it takes 4 subtractions of my common difference. Anyway, I may be over-explaining it based on what's there, but that's what this equation's saying. Now I'm going to write a simplified version of each term as well, meaning after I distribute the n minus 1. But what I need here, clearly, just like last time, I needed my common difference in my first term. Here I'm also going to need my common difference in first term, which we have. We have the first term is 35, and the common difference is negative 3. So the explicit function looks like f of n equals f of 1, 35, and the common difference minus 3 times n minus 1. And that would be it. But I promised I would show you the simplified form as well. I'm going to go ahead and distribute the negative 3 into n and negative 1. So it could also look like f of n equals 35 minus 3n plus 3. Remember, negative times negative. And 35 plus 3 is 38. So that's going to be negative 3n plus 38. And I'm going to write it in with the n term first in this case here, because it looks kind of like slope-intercept form. And I think that's kind of a nice key thing to talk about there. So I'm going to keep this thing with me the whole time. There is a way to write this thing, but it involves writing what's called f of 0, the 0th term. And I'm not going to have a memorizing stance from that. What I'm going to do is always make mention to these. And then I can always create it by distributing if needed. So anyway, that was a longer version of that problem. As I said before, I'll be faster with the other ones. Now that we've done that, let's go ahead and move on. Number 5. Whoop-oo. Again, arithmetic, they tell you that it is. Let's just go ahead and find out what it is that they're adding in case there's a weird typo. Looks like 7. So I got to get the recursive form and the explicit form. The common difference is 7, and the first term is 58. I need both of those things for both of these forms here. For the explicit form, for the recursive form, it's going to say f of n equals f of n minus 1 plus 7. We're starting at 58. F of 1 equals 58. Obviously, that's written right above, but for the sake of what I'm boxing, I want that to show up each time right there. The explicit form is going to say f of n equals first term being 58. We add 7, not the same number as the number of terms, but 1 time less. Okay, and it looks like that. If I wanted to clean this up and get the distributive form, the simplified version, distributing a 7 becomes 7n minus 7. 58 minus 7 is 51, so that becomes 7n plus 51. Okay. Maybe someday down the road I will actually explain how this one can be devised as well, but this one's got a little bit weirder of a story because you've got to start from 51, which is technically would have been a term before. But it still does work. I'm just going to keep it like this, though. All right, so there's the answer for number 5. See, that one a lot faster. Number 6, write a recursive rule again. Here we go. And like I said, I think the next 4 or so problems are all like this. So sorry if this becomes a little bit... If you want to move on from here, I think once I hit number 10 or so, the problems start to look a little different. So plus 16 each time here. I promised I'd bring the rules. Whoopsie. I promised I'd bring the rules over. Maybe I'll break that promise in a second. I want to see if we can remember what they mean in a bit. Common difference is 16. First term is 84. So recursive rule is going to look like f of n equals, starting from you take the value before it and you add 16 to it. And this is starting from 84. Okay, so it's going to look like that. Again, this always looks the same when it comes to arithmetic sequences. You're always adding the same number over and over, common difference. Right? That's how that would occur. An explicit function, to find the value of some term, use the term's position somehow. We're going to start with the first term, 84, and we're going to add our common difference of 16 and minus 1 times. Okay. If I distribute the 16, that's going to look like 16n minus 16, and 84 minus 16 is 68. So that's going to say 16n minus 68. I almost wrote 86. The one that I'm highlighting, though, of course, each time that I'm writing that, if you'd like to, there's that value below. But I'm really highlighting this one. However, when it does come, for me, if it comes to having to find, if they ask me to find the 100th term, I'd likely substitute it into here. So so if I have to simplify something, I likely will when I go about doing the problems. All right, number 7. Oh no, let's see. So this is one of those things where we might say something like, oh, I don't know what it's subtracting each time. What's interesting, what I'm looking at right here, look how the numbers change. Is this actually, this might be like a 1, 1, 1, 1 kind of thing. That's the only way these numbers can go like this. Notice 4, 5, 6, 7, 3, 4, 5, 6, 2, 3, 4, 5, 1, 2, 3, 4, and then just 1, 2, 3. Or like 0, 1, 2, 3. So I think 1,111 is being subtracted. I'm not certain, but let's check it out. To find out what we're doing from here to here, that's 1,234 plus D is 123. So I'm subtracting 1,234 from both sides. 1, 2, 3, 4. And I got to line up the things correctly. What I'll just do here is, you can do this with a calculator, but I'm going to do 1,234 minus 123, and then I'm just going to take the opposite answer. I'm just going to say it becomes negative, whatever this is. So we get 1, 1, 1, 1. So negative plus is that, if that helps you. So my common difference is negative 1,111. My first term is going to be 4,567. Never said they'd give you the smallest numbers. I did say this would get easier as you go through. Now, I'm not going to bring over the equations this time. Let's see if we can understand this one now. The recursive form. To find the next value, you take the value before it and you add your common difference, or in this case subtract, starting from your first term of 4,567. There we go. Oh, I don't want to box R with that. Let's just box this here. Okay. And then the explicit form, to find the value of any particular n value, we start from the first term, 4,567, and we're going to subtract our common difference one time less than the term position we're actually looking for. It looks like that. If I did distribute negative 1,111n plus 1,111, and I can only assume 4,567 plus 1,111 is 5,678. So I think it's going to be that right there. So two different versions of that form. Again, mostly highlighting that one right there. Okay. Number 8. Let's see if we can just do things without having to show any other stuff. Clearly, can we see this is arithmetic? They tell us it is. Looks like it's minus 25, right? So here comes recursive. F of n equals f of n minus 1 minus 25. I kind of want to live up to a promise of making this thing shorter if I can. Starting from 125. Again, once you've learned some of these things, it gets a little faster once you do this more and more. Explicit, this is recursive. Explicit now is going to be f of n equals the first term, 125, minus 25, one less time than the term we're looking for. Remember, if it was 25n, I'd be multiplying by 25 the same number of times as the number of terms I have. If that kind of makes sense when I say one less time. One time less. If I distributed the negative 25, it would be negative 25n plus 150. And again, I want to give it that slope-intercept form look, that y equals mx plus b look. It's not required, but I'm always going to write it that way. You might write 150 minus 25n. That's fine. These are both explicit. Okay, here we go. Number 9. You know what? I want to read what these things say. I didn't read any of these. Week and account. Sorry, let me go back for a second. Delivery number and the weight of the truck. So it's unloading 1,111 pounds each delivery, and you're depositing $16 every month, and the total cost of tickets here was $7 after tickets total cost. Maybe this is like going to a theme park and the entry fee itself, maybe like $51, and then you got to pay $7 a ticket for the number of tickets that you want, something like that. And then this one here, skaters in charge for a lesson. So again, maybe a sign up with the actual company that charges for lessons, so it's going to cost some money to begin with, and then it looks like it's $20 a lesson. So for number 9 here, common difference of 20, first term being 60. Now again, 60 probably wouldn't be the sign-up fee. I'm guessing 40 would, because it's 20 less. That's like without doing any lessons yet. And again, that 40 is going to show up in my explicit form if I simplify. But here we go. For the recursive form, we're going to get the value of the next term is the value of the term before it plus 20. And we're going to start from 60 to be doing that. 60 plus 20 is 80. 80 plus 20 is 100. Yada, yada. That's what recursive tells you. And the explicit form, and I sure hope they're going to ask me to find numbers of certain terms. That way I can tell you why explicit form can be nice and dandy. I know we did that in the last section, but now that we're creating the equations, I want you to provide value for why both of these might want to be written. So this other one, I start from the first term of 60, and I'm going to add 20. Once again, one less time than the numbers that I do it. To show that in full, that's going to be distribute 20, and that's going to be 20n plus 40 when I combine like terms. So there's that 40 that I promised that would show up right there. I kind of hope that's the last of those problems here. Let's see if we can move on. Okay, yeah, they are. Write an explicit and recursive rule for each arithmetic sequence. Okay, they kind of didn't go away. Now the thing is, they're written just as a list, not with the table. Nothing has changed though. There's still common difference, and by the way, there's a number 15 back here. There's still a common difference, and there's still a first term, and I'm still using that here. Again, for the sake of speed, let's go straight through. I'm just going to write recursive on top. So recursive is top, explicit is bottom. How about that? Recursive. Find the value of the next term and take the term before it. And it looks like we're going to subtract 5. We're starting from 95. Okay? The explicit, I'm just going to write the first one without distributing, if that's cool, just because of room and time. I start from 95, and I'm going to subtract 5 one less time than the value before. Again, this doesn't seem to ever change. How that's working there. Number 11, common difference of 7, first term of 63. So it's going to look like f of n minus 1. I don't feel great about this video that I'm doing right here when it comes to, I'm kind of just giving answers. There isn't much to what I can provide at this point, because this is a little bit redundant with regard to the problems. And then also, there's not much that they're asking me to do with them. Yes, we're writing the equations, but we're not using the equations right now to do anything with them, if that makes sense. They're not asking me to write out the next 3 terms or find the value of the 50th term or anything like that. I feel like there'd be much more use if I got to write these equations and do something with them. But they're not asking me, so I won't do them. All right, common difference of 15 here. First term being 86. Recursive on top, take the value of the term before it and add 15. We're going to start from 86 to do that. But I'm going to keep saying that stuff out loud because I feel like, those who have trouble doing this might not understand what any of this is saying. And I'm saying it as I write it. To find the value of the next term, take the value of the term before it, and add your common difference of 15. So take this, add 15, boom. Take this, add 15, boom. That's what recursion is, the value of the term before. To find the value of any nth term right here, you start from 86, and you add 15 one less time than the term number you're looking for. If I was looking for the 100th term, I would add 15 99 times from 86. That's that. Common difference of -2, starting from 112. So to find the value of my next term, I take the value of the term before it, and I subtract 2. Of course, we are starting, from 112. I think in the book and on a lot of worksheets, they'll show this part first. That they're going to write that beforehand. It doesn't matter. I'm more privy to writing the rule first than the actual term we start from, but again, it doesn't matter. And right here, the recursive rule is 112 minus 2 times n minus 1. What would be really nifty as well is that, we're transcoding from the list of numbers into the actual equations here. It would be nice to get an explicit, I don't know what problems come up next here, I cannot remember, but to get an explicit rule and to have to write a recursive based on it, or to write sequence terms based on it, and vice versa. Because as you can probably tell at this point now, it is possible it is actually possible to take one of these equations and make the other one. You can see these numbers appear right here and right here. So it's possible to go from one to the other if you want to go ahead and take advantage of one from the other as best as possible. Because recursive has a better benefit than explicit in some ways, and explicit has a better benefit than recursive in some ways as well. Okay, number 14. Common difference of 4. First term is 5. So the recursive form, I take the value before it, and I go ahead and add 4 each time, starting from 5. And the explicit form, starting from 5, I'm going to add my common difference 1 less time than the term that I'm looking for. Last one looks like a common difference of negative 30, subtracting 30 each time, starting from 67. So I will do f of n minus 1 minus 30, starting from 67. So again, this is acting more as an answer key. You know, I kind of feel bad in that front. Sometimes the homework isn't the greatest with that. But I do promise to do all the problems, especially if I diversify it a little bit for my class and say, now it's time to do the evens, now it's time to do the odds, something like that. So I am going to try and do all the problems for the most part regardless anyway. Hopefully that's starting to make sense once you see that tie in there, starting from 67, subtract 30, 1 less time than the number before. And that's it for those problems here. Let's move on and see what's next. Okay, maybe a little different. Write an explicit rule only. So we're only going to be doing the one where it's like using n instead of f of n minus 1. A student loan needs to be paid off beginning the first year after graduation. So when you graduate, you don't have to pay off anything. The first year after, you have to start the beginning. The beginning of year 1, there's $52,000 remaining to be paid. The graduate makes regular payments of $8,000 each year. The graph shows the sequence. So they actually helped you more than hurt you by showing this thing. Notice these are in thousands of dollars. So 52 is 52 times 1,000, 52,000, 44,000. So it's not just $52, if that makes sense. And these are years right here. So them telling you this information is great, I guess, on that end. I'm just going to go ahead and use the same thing that they do. If x is also n and y is also f of n, I will be using the number 8 or negative 8 instead of 8,000 because this is already in thousands right here. Okay, so f of n is in thousands of dollars. So to write my explicit form here, to find the value of my next term, to find the value of any year that I'm using, what I'm going to do is start with the 52,000, or I just write 52, and I'm going to take away 8,000 every year here. But to find the very specific year that I'm looking for, if I wanted to find it after year 6, I would only subtract 8 5 times. Because again, I'm already on the first year when I say 52. So I just got to subtract it 5 more times to get to 6. So that can be the function right there. Or alternatively, if I distribute the negative 8, it would look like 52 minus 8n plus 8, which is negative 8n plus 60. And again, writing it kind of in that slope-intercept form appearance, these are both the explicit rule, either or. Simplified, unsimplified. But again, telling the better story. All right, 17, I still have 5 more problems. A grocery cart is 38 inches long. Okay. Hang on, this thing's kind of cut off here by my face. Sorry about that. Let me move that up. There we go. A grocery cart is 38 inches long. When the grocery carts are put away in a nested row, oh, I get it. The length of the row depends on how many carts are nested together. So you probably know what I'm talking about here. If you have a grocery shopping cart, that's like that, when you push another one in there, it nestles in a little bit. It doesn't go right on top, but it nestles in just a little bit here, and it kind of goes in like, maybe like that. And then another one goes in like that. So the first one being 38 inches long kind of matters because that kind of starts off your length process. And the ones after that only add a little bit, 12 more inches each time. This is actually kind of cool drawing. So even though the first one's 38, every time after you're just adding 12 and 12 and 12 like that. That's kind of cool. So after one cart, it's 38 inches. 0 carts, it's 0 inches, but that's not a part of the sequence. That doesn't matter there. That doesn't matter. Graph shows the sequence there just like that, again, with the linear function doing the thing. Pretty cool. I kind of like the idea of bringing that up. All right, But we do need the sequence in explicit rule. I think all these are explicit here. I don't think they're going to be recursive. So we start. So our first term is 38 inches here. Our first term. Our first value. 38 inches long for one cart. For every subsequent cart, we're adding 12 inches. So to find the value of a certain cart number of the whole length, we're going to add 12 one less time than the number we're looking at. So you can write it like that. Or if I distribute the 12, I got 12n minus 12. 38 minus 12 is 26. That becomes 12n plus 26. One or the other, totally fine. Both the explicit rule. I really want them to ask us to find the value of like cart number 10. How long it is. I feel bad that you're not being asked this stuff here. I think section 4.3 does that. I think the next section that we do does do that. Number 18, a dog food for overweight dogs claims that a dog weighing 85 pounds will lose about 2 pounds per week for the first 4 weeks. The graph shows the sequence. So after 1 week, it lost 2 pounds, so it's now 83 and 81, etc. That looks weird having the coordinate pairs on top of and below each other. Let's go ahead and do this. Losing 2 pounds each week is the common difference, starting from 83. Technically, this is where I feel like this thing wants you to kind of write different rules from this. Because did we start from 83 or did we start from 85? And this is kind of where the kicker comes in here. Maybe I should write the other equation to really give you the idea. See, when we're writing our previous equation here, we're starting from the first term. And in a sequence, the first term is at a position of n equals 1. I think I mentioned this in my last video too. We do not start at n equals 0. We may theoretically have an idea for it, like the dog with the 85 pounds is when it starts off. That's n equals 0. But at n equals 1, the dog weighs 83 pounds. That's 1 week later. So I'm technically starting from 83. But, when it comes to that other equation that I've been talking about, because yes, this equation should look like this. Minus 2 times n minus 1 like that, right? But when it comes to talking about this thing, they're really kind of talking about starting from 85 pounds here. And for every subsequent week, you're going to lose 2 pounds. I get that, and this equation's fine. But if you want the one that uses the number 85, this is where you do that simplified thing. This is where we distribute the negative 2, and then we get 83 minus 2n plus 2, and 83 plus 2 is 85. So that's where we get, and maybe me not even writing this in the slope-intercept version will make a little more sense to you. 85 minus 2n, negative 2n plus 85, or 85 minus 2n. Maybe this equation bodes better. They're both the same thing. These both give you the same answer if I plug in a number for n. Make no mistake, these are the exact same thing. When it comes to the explicit rule here, it looks like the 85 being told in context kind of gives you a better understanding of what you're saying. I'm going to start from 85 pounds, not that it's one of the weeks, not that it's one of the terms in the list, but the dog starts at 85 pounds. And everything I'm going to list is based on the number of weeks since then. So after 1 week, he loses 2 pounds. 1 week, 2 times 1 is 2. 5 weeks, 2 times 5 is 10. 10. It's going to lose 10 pounds. So you just plug in the number of weeks from this one. Maybe that one is a little better feeling when you write that equation. And I should maybe sometimes speak more on this. There are old videos that I have, without me on camera, there are old videos that I have where I speak in terms of this. I use this form. I use my f of 0 instead of my f of 1, if you will. Because that's when I start to introduce slope-intercept form, or we've already done it in the past. So this is a little newer for me to state each time. But I do like this more in the sense of it's less of a memorization tactic. But I like this more in the sense of it gets you into that linear form as well. And sometimes problems are better explained this way. There it is. Either one works, though. Either one works. Okay, number 19. A savings account is open with $6,300. Monthly deposits of $1,100 are made. The graph shows the sequence. So kind of the same thing as the dog one, right? We do start at $6,300, but that's not a value in our sequence. Sequence does start at the first term, never at the 0th term, even though there's a theoretical 0th term. So let's go and write this one out. I'll write it in good old lovely red. Sequence, I'm starting technically at 74. Remember, the f of n is the hundreds of dollars they're showing here. 7,400. Starting at $7,400. I'm going to add $1,100. One time less than the than the month I'm looking for. So like that, if I did want to write the 63 with it, remember distributing the 11 will kind of show you that 63. 74 plus 11n minus 11 is 63 there. So f of n equals 11n plus 63. Either or works out. If you have questions about this stuff, please write in the comments section. Some people are asking, maybe ask, why are you writing both of these things out? When should I use one versus the other? Should I be writing both? The answer, should you be writing both? Not necessarily. But if this is how you construct all of yours and you need to write it based on that, I guess both need to be written. Should he be? No. I'm giving everybody their option, however you guys choose to write it. Number 20, the wolf population in the local wildlife area is currently 12. Notice there's no graph this time. Due to a new conservative effort, conservationists hope the wolf population will increase by 2 animals each year for the next 50 years. Assume the plan will be successful. Meaning, assume this will be basically an arithmetic sequence. Assume 2 animals each year. Write an explicit rule for the population sequence. Use the rule. Good, I love this. Use the rule to predict the number of animals in the wildlife in the 50th year. Yes, they're actually asking us to do something with this. Thank goodness, I've been waiting for this. All right. We start at 12, but we start at 12 when this thing is like starting. F of 0, the 0th term is 12. We do not know the first term yet. 12 does not exist in our sequence. 12 is not the first term. This is the first term. Okay, so we use, in theory, the idea, the conservationist hopes 2 animals of increase each year. So 12 plus 2 will give us our first term. 12 plus 2 is 14. So when you write this equation, again, it can come in one of 2 forms, either using the first term or ideally the 0th term. I'm going to give you the first term first, and then I'll use it to grab the 0th term later. But using this to find that first term is the number 1 goal. So we go ahead and say f of n equals, starting from 14, we're going to add 2 wolves every year, but to find a certain value, we'd add 2 one time less than the number of times, If I want to distribute this in combined like terms, it would say f of n equals 2n plus 12. And again, you can see where that 12 kind of comes from. The 12 is the 0th term, if you will. Starting from 12 wolves, I'm going to add 2 wolves every year for the certain number of years that I do. So if we're going to go ahead and find the 50th year here, I'll do this in blue just like that. F of 50, I can use either equation. This is where I said I'm more likely to use this equation than not. It does depend on the number they give you, but I'd rather do 2 times 50 than 2 times 49. So why don't I just do this one? 2 times 50 plus 12, that equals 100, plus 12, which is 112 wolves. We are predicting there will be 112 wolves after in the local wildlife area after 50 years. Starting from 12, 100 wolves later, 50 years later. All right, got one last problem for you. Right on schedule, 43 minutes here. How are the terms in the sequence in the table related? Is the sequence an arithmetic sequence? Explain. So first things first, not arithmetic, right? We're not adding a common difference here. However, and you might notice this, you might say something like, oh, plus 6, oh, plus 18, oh, plus 64. Is that 64? No, plus 54. Oh, plus 54. And you might say something like, hey, I see a pattern. Maybe you do. I do. It's kind of a strange one. I don't know how to explain this, but check this thing out. 1 second. First, let me figure out this number. Plus 162. And these numbers are separated by, take a look at this, plus 12. And then this is plus 36. And this is plus 108. There's something to this common difference here, that these common differences eventually land on a common difference within itself. I think I'm going full bore into something that I shouldn't be explaining right here. So anyway, no common difference. Okay, no common difference. But maybe it's not about addition or subtraction. Maybe it's about multiplication. I'm multiplying by 3 each time. You see that? You can probably trust it afterward, but it's multiplying by 3 each time. So not arithmetic, but it has what's called a common multiplier or a common ratio. it has common ratio. This makes it what's called a geometric sequence. I'm focusing on arithmetic sequences right now. Someday I'll go into geometric sequences and we'll talk about these. We'll get their equations in recursive and explicit form as well. But that's the description. You don't have to say geometric sequence, but it does have a common ratio. You're multiplying by 3 each time. And that's what it's doing instead. All right, so I hit my 45-minute mark there. That's going to be it for this video. My name is Mr. Robinson. Sorry for kind of the redundancy in this one. I wish they asked more questions like number 20 in terms of using your equation to get something out of it. But you know what? You're practicing little things. I hope you now understand how to write the recursive and explicit rule after you've seen a lot of these problems. And if you do have more questions, please write them down in the comment section below and make sure you ask me. All right, guys. Happy Sunday. Happy football Sunday. Have a great day. Bye.